I thought today we can talk about how Pyrefly thought about implementing third-party support. I'm going to talk about specifically how we supported Pydantic and Django. Um, this was work that I designed while on Pyrefly, very closely with Rebecca. And so I'm going to talk about the design philosophy that we did and how we approached the problem, as well as some of the open questions that were still there after we rolled out the support.
And I'll be talking about kind of how we supported attrs in Pyrefly and exploring how we can reduce special casing and looking at a little bit into PEP 827.
Yeah, so initially when we started, MyPy was at the time the only type checker that provided third-party library support, and it did that via a plugin system. We wanted to move away from that because we got feedback that the plugin system was fragile, it exposed the type checker internals, it crashed. So there were some downsides to it. It also required setup. And so the ecosystem was starting to move away from that. And so we wanted to do off-the-shelf support. And so for the support we needed it to have certain qualities. So of course it had to be as much as possible sound. And by that, if our library that we're trying to support is typed, of course we consider those types. If not, then we can look into stubs. So we'll talk about exactly what we did there later. The other thing is we wanted to work out of the box, like we said, to not have any complicated setup. And we also didn't want any perf regressions. We wanted it to be fast. So we'll see later how some features can impose perf issues. And for those, we have to make a choice to avoid them or limit the support. And we wanted to scale to large code bases. So that means that the set of features that we pick has to work for most code. So the average user, they're writing using the third-party library. We want most features to work for them. Okay, so we said that we want to use existing types. So for Pydantic, for example, the library is typed. So of course we want to go to the definitions. We want to be able to read those types and incorporate them into our checking. For Django, it was not typed. So we had to figure out stubs. And for that, we chose Django stubs. It's a community maintained library. It was well supported. So we had to make a choice there. And so for the design philosophy, I will give an example. So for example, Pydantic, we have this thing called a base model, right? That's the basic Pydantic model. If we look at the actual definition of it, we'll see that it's decorated with a data class transform. So we already have data class transform support. So what we wanted to do is we want to ensure that that data class transform support is, of course, complete to begin with. And then there are going to be additional features that are specific to just Pydantic, which we'll go over. And so we want to make sure that we're really supporting, as much as possible, we're going through the same code path and only diverging on those differences. So I'll give an example later. But we did use basically the data class transform like code path for Pydantic. And then for Django, it's just the class pipeline. So we process the classes as usual and only inject Django logic when there's a diversion. So we will also see. And that way we want to keep things as separate as possible and don't want to inject too many code paths. So here's an example. So for Pydantic, we see here that this is a Pydantic class C. It inherits from a base model. We process the base model because it's a typed piece of code. And then we essentially extract some metadata specific to Pydantic. We add it to the data class metadata. And then from there, we inject additional logic when we start generating, for example, more functions. Django was the similar story. So we again inject some Django metadata into the regular class pipeline. And then when it comes time, let's say, to process fields that are specific to Django, we inject just that logic into the field generation process for regular classes. But we keep everything isolated. So the piece of code that processes Django fields is isolated, but it's injected only when we need it. So yeah, I think we can skip this. Okay, so to give a concrete example, so Pydantic, how does it differ from regular data classes? One place where it differs is that Pydantic is not just a data class, it provides also runtime validation. So for example, a normal data class here, so we have class A, it has a field integer, and it's calling X with a string. So of course, string is not compatible with integer. And so in normal data classes, we would get an error, a type error, if we were to use Pyrefly, let's say. But in Pydantic, they allow runtime coercion because it is a runtime validation library. So this program actually would type check. So how do we support that with our design philosophy? So in Pydantic, right, you can actually specify strictness with a keyword. So this strict equals true keyword here. You can use it to say that you allow runtime coercion or you forbid runtime coercion. So what we did is essentially this is data class code, or it will act like data class code. So we process it as such in Pyrefly, seeing that base model was a data class transform. So then what we do with this strict keyword is we lift it to become a data class keyword, and then we turn it off by default, and then turn it on by default for data classes and off by default for Pydantic. So that's how we kind of do the support. We lift things to generalize them when we can, and then again we diverge or maybe set certain defaults based on whether we're Pydantic or whether we're a normal data class. And of course, we had already stored this in the metadata, so we can tell when we need to. The same idea applies to Django. So we did choose Django stubs, like we said, because it was well maintained. And so we process the stubs to extract types. So we can go to next. So for example, here is a class reporter. It has a name. This name is this models.character field. This is read from the stubs. So that means we go process the stubs and we extract the type, and we are able to type check this example. Django also comes with synthesized fields. So again, like we were saying, we inject that field functionality when we need it, because we know that we inject it when we need it because we had already processed that this is, for example, a Django class. Okay, so there were a few limitations when it came to the support. Some features were left out. So one example is the Django reverse relations. That one is basically required us to scan the whole program and visit potentially multiple files to understand or type check this relation, and that could impose a performance overhead. So that is an example of something we left out, and MyPy was supporting it by looking at runtime information and by looking at the whole project structure. Another example is this alias generation functionality. So what this does is it generates alias names, but like with a function. So you'd have to run the function to know the alias name. That didn't quite suit sort of how we handle just static typing. So this was something where we had to pause and like kind of leave it for later. But the plugin system, could support. So that's where there's a difference. So I think the two open questions here are, first of all, there was a long tail of features. So we focused initially on core functionalities that are commonly used. How can we efficiently support a long list of features in Pyrefly? The second thing is, every library that we add, even though we did our best to minimize the code paths and to keep everything uh, contained and isolated as much as possible, it did require a bespoke path after all. And so with every library we add, we still do have to give that extra code path. And also there's a maintainability cost. So the open question was like, how can we eliminate or mitigate that issue?
Yeah, so moving into kind of the third-party library that Pyrefly supported. So Pyrefly supported the attrs library, and attrs is a really popular library, and it kind of predates data classes, so it kind of has more features. And so here's kind of a small example of how we use attrs. So we can use like the attrs define decorator to declare this class as an attrs class, and then in one of the parameters in attrs that define it defaults to auto attributes is equal to true. So for any annotated attribute in a class, that automatically becomes an attrs attribute, and then we can also specify something to be an attrs attribute with the attrs.field keyword, and then we can add more specific features to this attrs field, like adding default values, adding validators, adding converters, aliases, and other types. And we can also add other features, like we can add validators that are outside of the actual attribute annotation section. So we can add like a decorator x.validator, and we can add more specification there. And also we can there's another feature that attrs has where we can do attrs.evolve, and it basically copies a current attrs class, and it renames, or it replaces some attributes to other attributes. So as Zita mentioned, the first two libraries use data class transform as like the main code path, and we diverge only when there's special casing. And so attrs also does this same thing too. Like for all the data class transform features, it goes to the same code path, and then where it diverges, we have our own like attrs specific files that do specific handling. And it turns out there's like a wide variety of things we had to special case. So like converters, validators, copy constructors, and there's a lot of things we had to special case, and it turned out to be around like kind of 1,100 to 1,200 lines of code for special casing logic, and this logic is very useful to providing support for attrs, but at the same time, like other type checkers, can't support attrs. This doesn't really benefit other third-party libraries, and as Zena mentioned, we also support Pydantic and Django, and then we have attrs. So kind of the natural question is like that comes up is we special case so much. Are there ways to kind of make the special casing more easier, or more easier for type checkers to kind of work for free? And so we kind of looked at a lot of things online, and we found Pepe 27. We found, which was really interesting, which kind of introduces type manipulation and type transformations. So just like a brief difference between like right now, each checker hard codes library knowledge. Like Pyrefly, we support Django, Pydantic, and attrs, and while some other libraries use plugins for that, and some other type checkers use plugins for that, and some other type checkers don't even provide support for this. So this kind of disparity is pretty bad, I feel like, in terms of type checking space. And there's going to be a lot of diverging behaviors and like a lot of unsound behaviors that Zena mentioned. We want to we want to make type checkers across the board be really sound, and also new libraries go unsupported. So if there's like a new library that looks pretty popular, but it has a lot of runtime magic and a lot of meta class behavior that's not currently supported by type checkers, it's going to be pretty bad from like a user experience, and also right now like an agent's experience for actually debugging code at type check time, at static time, and trying to fix errors before we actually run the code, because that could be pretty costly. And so with Pepe 27, this is what we think is a good step forward in terms of like generalizing type manipulations. So we think that like libraries could declare their own transformations in their own like libraries or in their own type stubs, and because of this, it's going to be one standard protocol, and new libraries would work kind of for free if they implement or add type manipulations in their code. And of course, type checkers also have to provide support for Pepe 27. And then another benefit is it's going to be consistent across all checkers, which is good for trying to um, trying to like analyze your code with different type checkers. So kind of like what Pepe 27 adds, it's a really big pep, and it also has like sub pep um, proposals. So it kind of breaks it up into two things where we can inspect a class at type check time and also construct types at type check time. So like, for example, we have um, attrs T and members T, and this basically returns kind of a list of each like member in a class. And like a member could include like an attribute, or it can include like a member function or a function. And then attrs T would just represent like the attributes. So kind of in companion with this, we can iterate through all these attributes, and then provide um, um, more specific types to some of these attributes based on how the library maintainer wants the types to be, because there's a lot of magic that goes on in runtime. And for the second part, we can construct new types. So like once we iterate through some certain types, we can construct new types. And this PEP also introduced like notion of extended callables, where we can create a new params list with more specific information. And so here's kind of an example with attrs.evolve. So right now, the stub is just it has an instance with underscore t, and then has kwargs, keyword argument changes type to be any. So this right now isn't really helpful for providing static type checking. So of course we had to special case this. And then so with PEP 27, this is like a um, proposed thing that could be in the stub, where we create a type alias called evolve function, and then it returns, or the type is a callable or an extended callable, and then I'll go more in depth here. So it would be a callable, and then it would iterate through all the params or the attributes in a class with typing.attrs t, and then it makes sure to see that if the init field in attrs is not false, because um, we can't update a value based on the runtime semantics of attrs.evolve. We can't update a value if it's not in the init field. So we can do that on if not typing dot is assignable literal false. And a lot of these like typing primitives are introduced in Pepe 27, and so we can kind of construct like a new and more specific type stub. So this is an unpack operator, and it unpacks each param. And so this after we do all that, so in step 4, we can see like the computed signature here it would be like an instance of type point, and then the rest would be keyword arguments, which matches what the runtime semantics of what attrs does for attrs.evolve. And we can see here how like the library maintainer could possibly declare their own type transformation. And so if checkers implement Pepe 27 or something similar, they would be able to synthesize this method, and then check do more accurate checking at type check time. And so kind of the path forward, we think Pepe 27 is a really good direction, but it looks like a really ambitious PEP, like coming from a person like an intern who only has like 1.5 months of like Python typing. Like it's like a lot of it is really interesting, but at the same time it looks ambitious. So like there are some kind of goals or discussion topics we can talk about after, about like maybe trying to improve just like data class transform to add more features, or implementing things similar to data class transform that we see that are common occurrences in other libraries. And so yeah, I just want to thank you guys for showing up, and I want to thank Stephen for hosting this typing meetup. But yeah, we have time for questions and discussion. So.
Great. Yeah, thanks for the presentation. I think we can open it up for any discussion. I was somewhat hoping that some TY folks would be here because I know they've cared a lot about this exact question of supporting the library ecosystem. But we still have a few people. Anyone have thoughts? I guess Sebastian in particular, I know you do a lot of typeshed work. I don't know how exposed any of that is to MyPy plugins.
Yeah, of course. I mean, any kind of power to type annotations is of course very useful for the different kind of steps that we have. And when I look at some of the annotations where we have to use any quite often for things that probably could be determined during type check time, but there just isn't the power to do that currently in the typing system. I could see transformations like that to be very useful.
Martin?
Yeah, so I went through PEP A27, like this is something I've been thinking about for a while too, and again, I think this is going in the wrong direction because these types, like these extremely complicated and extended types, have very little human readable value, and so having them inline as type annotations, I think is the wrong way to go. What we should be aiming for is a sort of universal language for writing plugins in that various type checkers can add a mini interpreter for, which would allow package maintainers to just write their plugin in this sort of typing implementation language, but would not be constrained by the subset of Python that we can stuff into a type annotation. It would be a lot more pleasant to maintain. It would not clutter up your source code. And I mean, the only people who do care about it are the type checkers, and they do not need to read it in line in the source.
Yeah, it's an interesting idea that has come up. For what it's worth, I'm not sure, not everyone here was at the Typing Summit, but we are looking at supporting integer arithmetic and shape types in Pyrefly, and we've gone stronger in that direction of a functional form for type manipulations. Partly, I think it's because some of the shape manipulations are more complicated than we can work out expression syntax for. I don't have strong opinions about the trade-offs, but I do think it's worth noting that, like, for composability reasons, we've kind of gone a statement and functions route there. The goals are abstractly very similar to A27. It's a totally disjoint set of typing behaviors we're trying to implement, but the problem of needing more than we can get in closed form is kind of the same. My impression, though, is that discussion on 827 has been pretty positive to date. I don't know. It's an interesting question, but I guess we would need to raise that if we want to consider alternatives to expression syntax in the discussion of the actual PEP. They did discuss it. It's in the rejected alternatives section, I believe, thinking about more of a statement-oriented approach.
I wonder, so like one reason that we didn't support MyPy plugins in Pyrefly is because now we have to keep Pyrefly in line with a potentially brittle API that's like requiring some expressiveness that we might not need. I wonder why that problem doesn't come up as much with 827. Like it seems like this is very, very similar to some sort of like plugin system, but just written as a type annotation. Are there features of PEP 827 that make it easier maybe for type checker maintainers to use than a plugin system would?
I guess my initial reaction is that it's specified, whereas I don't think MyPy plugins are specified at all. And I think they're coupled to MyPy internals.
Makes sense. So just by forcing everyone along the same route, Pyrefly or other type checkers that use 827 will not have to veer too far from other checkers, and then changes to the type system will hopefully work well with it, is kind of the big reason.
That's my read. Anyone else is welcome to chime in, but that's at least how I view 827 and how it can expand things.
Yeah, I feel like I personally feel like giving the ability for like library maintainers to add those types of like type checking expressions and manipulations in their own libraries, and then would be better in as opposed to just like special casing it or adding a plugin for only one type checker. So
makes sense. Shobit, I have a question for you. Having implemented attrs support, do you think there is a feature you found in attrs that might make you more likely to use it than data classes in your own Python programs?
that's a really good question. So I think like attrs has a lot of like it's more extendable, and it's like has more of a rich feature set. I personally have not written a lot of Python code in like projects, but I feel like there I don't know, I feel like the feature set is more advanced enough such that if I ever need to use some features that are not in data classes and that are in attrs, I would move over to attrs. But like I don't have like a exact answer for that question. Makes sense.
This may be out of date, but I also believe Geo once looked at this and concluded there's a significant perf advantage to attrs, which may be driving some of the adoption. Any more thoughts? I think one thing we could do as a follow-up is, I think, Shobit, some of your explorations of how PEP 827 applies here could be relevant to the discussion of that PEP, and it might be worth posting in the appropriate thread on Discourse. We could link the slides or link to the meetup, which should have a video of our presentation here. And I guess the same is true for Martin, if you have concerns that haven't been raised. Like ultimately, the discussion of that PEP is, I think, a Discourse thread primarily. Is that correct, Rebecca? Just to double check myself.
Yeah. Yeah, it's on Discourse.
Cool. If there's nothing else, we can wrap up, I think. But yeah, I appreciate the presentation and the work, especially exploring how an open PEP potentially applies to the problem we've spent a lot of time on here. Hopefully this will help the whole community move together in the long run. Anything else?
I just want to thank you for organizing the meetup. We haven't had one in a long time, and I appreciate that.
Yeah, thanks. Also, if you have topics, I keep getting busy and forgetting, but like I intend to post a call for topics every month. There were a lot of months where we had no topics, which is part of how I fell out of the habit. And then in the run up to PyCon, I never really have time, but cool. Take care, everyone. Have a good Wednesday.